Okay, so today we'll start about the week 4 lecture topics. So I have prepared some questions on the week 4 lectures. So let's start. So first question is, how do the kinetics of sorry, precipitate formation differ between natural and artificial aging, and why does this impact the eventual precipitate morphology? So first we know that the aging is to keep the material at the temperature, to keep a supersaturated solid solution of aluminum alloy of an age hardenable aluminum alloy. So if we do aging at room temperature, that is called a natural aging. So if it is at room temperature, then it is natural aging. While if we keep that supersaturated solution at a certain high temperature. So this temperature is around 100 to 300 degrees Celsius, not more than this. So this is called as artificial aging. So aging means the uh, supersaturated solution as it comes to room temperature or a lower temperature, then this its solubility limit. So the extra solute atoms starts to precipitate out from the aluminum matrix. So first aluminum matrix form by rejecting extra solute atoms, and that extra solute atom arrange in some arrange, order to form some precipitate particles. So those precipitate particles need some type of diffusion to make a cluster. So, for diffusion, we know that the diffusion increases it at high temperature. And in natural aging, the solute atom diffusion is slower. Diffusion is slow, and at high temperature, diffusion is faster. So, because diffusion is slow at room temperature, the atoms will take time to make a cluster, and uh, the ordering of that is also will not be so because diffusion is slow, the most favorable solidific arrangement plane they arrange. So the morphology can be rough and irregular. But in high temperature, diffusion is faster. So more number of atoms can come from every direction to make the cluster and form the precipitate. So the morphology, because diffusion rate is high, so morphology of precipitate will be close to spherical. Or and if it is going to so with the age, with aging time it can differ also, means it's from spherical to rod or flake type. That depends on the time and temperature, but some a specific type of morphology of these precipitates we get at high temperature or artificial aging. Okay, so next question is explain the transition from GP zones to equilibrium precipitates. What metallurgical instability drives this solute rejection process after quenching? So after quenching means we heat the material to dissolve the solute atoms completely in the aluminum matrix. Then quenching make the supersaturated solution, solute solution. Then after quenching, we keep the material at room temperature or high temperature. So these cluster of solute atoms uh, arrange, like if we arrange in some order, means alternate solvent and solute atoms arrangement along a specific plane. Shrikant, can you see my screen? Okay, so I was discussing the questions regarding the week 4 lectures. So first is the how do the kinetics of precipitate formation differ between natural aging and artificial aging, and what does this impact the eventual precipitate morphology? So in aging, we keep a supersaturated solution of an age-hardenable aluminum alloy at either room temperature or high temperature. So room temperature aging is called natural aging, where high temperature aging is called artificial aging. So, in natural aging, we are doing at keep the sample at room temperature. So, in that condition, diffusion is slow. So, because of the diffusion, slow diffusion, the morphology of these precipitate will be rough and irregular. But while at high temperature, diffusion is faster, so more atoms can come from every direction to make the precipitate of spherical, rod, or flaky shape. So means a certain shape we will achieve with high temperature artificial aging. So next question is explain the transition from GP zones to equilibrium precipitate, and what metallurgical instability drives this solute rejection process after quenching. So quenching we do after solid solutions, supersaturated solid solution we achieve by heating the sample at high temperature to dissolve all solute atoms, and and after that we quench the material. So the precipitate or solute atoms start to arrange in some order. So that can be alternate solvent and solute atom arrangement along a specific solidification direction or a specific plane. So in that plane, that can be So the most favorable arrangement is along 110 direction. So in this direction, the spheric is on this plane and in along 100 direction. So the arrangement, the solute atoms arrange in some order and form the small cluster of the solute and solvent atoms. Then again, by growth of this cluster, GP zone is formed. So GP zones. So first we can write supersaturated solid solution. Then it forms GP zones. So GP zone is the arrangement of solvent and solute atoms along a specific plane, and after that, uh, as it grows, so this can we can call it as GP1, and with growth it transform into GP2, in which its thickness and diameter increases. Dia increases. And also we can say that this arrangement have coherency with the aluminum matrix, means the atom to atom matching we can observe between the aluminum matrix and this precipitate arrangement. So the coherent interface uh, is forms in GP zones, and is good it grows to GP2 zone by increasing its thickness and diameter. Then again it transforms into theta double prime, which is also coherent with the aluminum matrix. Then again, with growth of this theta double prime precipitate, the theta prime uh, precipitate form. So the theta prime precipitate is semi-coherent with aluminum matrix. Then there has to be some mismatch between the planes. And after theta prime, it when it further coarsen, so the equilibrium phase, which is theta, this is equilibrium phase, is formed after with time. So this equilibrium phase is incoherent with aluminum matrix, and also its size is also large compared to the GP zones and theta double prime precipitates. So, what metallurgical instability drives this solute rejection process after quenching? So, the metallurgical instability is that the solubility with decreasing temperature decreases. Solubility of solute atoms decreases with the decreasing at the low temperature. So, decrease in solute solubility, solutes of solute atoms at low temperature. So because of the solubility decreases, so that's why the solute rejected out from the aluminum matrix, because the aluminum can only have set very few, less concentration, so dissolved at the low temperature. So the extra solute atom reject out from the aluminum matrix. Okay, so next question is, what is the fundamental difference between natural aging and artificial aging in aluminum alloys? So, natural aging is we know that it is done at room temperature, and artificial is done at high temperature, around 100 to 300 degrees Celsius. Or 300 is also high. We can keep it up to 250 degrees Celsius. So the if we talk the transformation behavior in the natural and artificial aging is that the if we talk about this temperature and time. So this is at super cycle. So this is complete dissolution of the solute atoms. Then this is the transformation curve for the precipitate. So if yes, so this is the rate. So if this is done at a low quenching rate, so coarse precipitate is achieved. And if we do at higher quenching rate, so fine precipitates we obtain. Next is, yeah, so cooling rate effect comes in this. So fourth question is, why might an additional two digit sequence T651 be added to a standard temper designation, and what purpose does it serve? So T6 temper is the solution heat treatment uh, plus artificial aging, artificial done aging done up to peak hardness, and the further two digits 51 represents stress relieving by compression to remove uh, tensile residual stresses. So the two digits represents the stress relieving operation for that specific temper condition. So so this is done to remove the residual stress in the sample. The next question is, how does the cooling rate affect the formation of precipitates during the quenching stage? Yeah, so quenching stage, it is the temperature versus time transformation curve. So this is at the alpha where complete dissolution is achieved, and this is the transformation curve. So with if we do quenching at with low cooling rate. So low cooling rate will take this path. So in this, coarse precipitates are obtained. Why if we do very high cooling rate quenching, then it forms this. It follows this path. So with this path, the fine precipitates are formed. So also we can say that in natural aging and high temperature artificial aging, then in natural aging the precipitates are fine, and at artificial aging the precipitates are coarse. Next question is, what are GP zones and how do they contribute to the strengthening of an alloy during natural aging? So in natural aging, the cluster of atoms on certain planes are formed. Cluster of atoms on particular planes are called GP zones. And they have some coherent means coherency coherent interface with aluminum matrix. So because coherent interface is there, some little lattice mismatch will always present, and this lattice mismatch creates some type of coherency strain. So this coherency strain increases with decrease in coherency. So this coherency strain react with the dislocation movement, and it hinders this dislocation movement from this region from precipitate to aluminum, or from aluminum matrix to precipitate. The dislocation will have some difficulty in crossing these precipitates, so that coherency strain leads to the uh, hindrance of dislocation motion, and that contribute to strengthening of an alloy during natural aging. So in the natural aging, the cluster of atoms form very fine precipitates form, and this hamper the dislocation movement. So next question is, why does the hardness of an alloy typically decrease during the overaging stage? So in the overaging state means after GP zone formation, theta double prime form, and that with increasing time, theta prime form, and after that equilibrium phase, theta form. So theta is the coarser precipitate. So with fine precipitates, they are large in size. Sorry, they are their number density is higher. So because of the higher density of small fine precipitates, the uh, the dislocation motion is hindered to a very high level, and that increases the strength and hardness. So this results in high hardness. But with the time, these fine precipitates starts to collapse and form a coarser precipitates. So with the time, these precipitates coarser, and with coarsening, the number density reduces. This number density reduces, and because of the less number, the dislocation hindrance is less, and the hardness decreases. Next question is, what role does coherency strain play in hindering dislocation movement within the lattice? So coherency strain, uh, the between precipitate and matrix. So the precipitate interact with dislocation, and that interaction will result in some coherency strain. Epsilon, it is written as epsilon. So the strengthening, increase in applied stress with this coherency strain can be written as 6G R by B raised to power half, and F 1 by 2 epsilon 3 by 2. So G is the shear modulus, R is the precipitate radius, B is Berger vector, F is the fraction of precipitates, and epsilon is the coherency strain. So because of the interaction with dislocation, we have to apply more stress for to overcome the dislocation uh, hindrance. So this the coherency strain uh, means restrict the motion of dislocation from the aluminum matrix to the precipitate and increasing the uh, stress strength of the material. Then, what is the primary role of the modulus effect in precipitation hardening? So, modulus effect means the precipitate modulus is different from aluminum matrix. So, because of this different modulus, the local modulus changes, And because of this local modulus change, the dislocation, diffusion of these precipitates or solute atoms around the dislocation will be difficult. So energy of dislocation, because of this modulus change, energy of dislocation changes. Will change. And that further increases the strength of the aluminum alloy. So the increment in strength can be written as delta G by 2 pi square 3 of modulus of delta G by G B raised to power half and zero point 0.8 minus 0.143 R bar by B R square and F is power half. So this is the stress increase, strength increase due to the modulus effect. The next question is, how does the creation of a step at the particle matrix interface affect the material's strength? So particle matrix interface is that means when precipitates are small, so dislocation, small precipitates can be sheared by dislocation, sheared by moving dislocations, and that shared out this is a dislocation, this is precipitate. So the precipitate shear out like this. So the extra free surface is created on the precipitate particle. So this extra surface increases the energy, surface energy of the particle, and that surface energy will also contribute in further motion of the so hindrance of the dislocation motion. So because of this surface, new surface energy increases, surface energy gamma increases, and that further interact with dislocation motion. So the strength contribution from this particle matrix interface creation can be written as 2 times of square root of sigma by pi gamma s f by r. So gamma s is the surface energy and sigma is the applied stress, pi and f is the fraction and r is the radius of the precipitate. Next question is, what is the significance of interparticle spacing when dislocations bypass precipitate? So the small precipitates are sheared out with dislocation, but when the coarse precipitate faces the dislocation, so this is the two coarse precipitate and dislocation line is moving in this direction. So in the next step, it the dislocation line bow around the particle like this, and in the second step it tries to move out from the precipitate between these two precipitates. And after that, as it passes these coarser precipitates, the this this leave the dislocation loop around the particles. So this dislocation loop around these coarse particles will further inhibit the dislocation motion. So the distance between this, if we take as lambda, so this distance they will decide the interaction of dislocation with the these coarse particles. So as particle or precipitate grow, this lambda increases, the distance between the two precipitates increases, and the stress required for this condition is generally written as tau equals to GB by 2R. So here 2R is the distance between these two precipitates, means lambda equals to 2R. So it can be written as GB by lambda. So if spacing will be larger, then stress will decrease. And if spacing is low, then stress will be higher to move the dislocation from these precipitates. So next question is, in the aluminum copper alloy system, what is the sequence of precipitate formation from the supersaturated solid solution to the equilibrium phase? So in the aluminum copper system, we have two atoms, aluminum and copper. So in the initial stage, when the supersaturated solid solution of aluminum copper is aged, so first cluster of copper atoms form on 100 planes, and thickness of these cluster is around few interatomic distance. And dia is also few some thousand atoms, 100 or 1,000 atoms. So with aging, time increase as well with aging time, thickness and dia increases and reaches to a constant size. So at room temperature, if it is done, the size is 3 to 7 nanometer, and at high temperature, 100 degrees Celsius, thus 10 to 15 thickness is can be achieved. So in the next step, so the first cluster of atom is called the GP zone, GP1 zone. In the second step, where it grows further, so GP2 zones are formed by alternate aluminum and copper atoms on 100 plane, and thickness of it is around 10 atomic plane thickness, and its diameter is around, so it is thickness is around 4 nanometer. While so its shape is so GP2 zones are tetragonal crystals. In the third step, where GP2 zones further grow, so this up to this point, GP2 zones are coherent, and after that, theta. So GP2 zones are also written as theta double prime, and after theta double prime, theta prime forms. So this theta prime is plate shaped. So the and the shape of the plate depends on uh, aging temperature and time. On time and temperature. In the fourth step, where theta transforms into the theta, so it is equilibrium phase. So see, theta dash is CuAl2, and theta is also CuAl2, but it is now stable. So this is the equilibrium phase of CuAl2, and it is also tetragonal and incoherent. Okay, so the first GP1 zone forms with aluminum copper system with alternate arrangement of aluminum copper, sorry, with copper atom cluster. In the GP2 zones, the aluminum copper atoms alternately arranged to form the tetragonal precipitates. In the third step, this tetragonal shape further transform into the plate shape of CuAl2. Then after, so this plate shape theta dash is the semi-coherent, but with further growth, it transforms into the theta, and it is the theta is the equilibrium phase with tetragonal and incoherent interface. The next question is, what are the key stages in the precipitation sequence for aluminum copper alloy before reaching the equilibrium phase? So it is supersaturated solid solution of aluminum copper, then GP1 zone of, so this is the cluster of copper atoms, and GP2 zones is the alternate aluminum copper atoms. Then after this point, So this is the theta double dash. Theta dash form, which is tetragonal shape and semi-coherent. Tetragonal plate shape with the semi-coherent interface. And after that, theta equilibrium phase form, CuAl2. So this is the incoherent. So next question is, how does the aging temperature influence the final size of GP zones? So with aging, the temp with increasing temperature, the size of GP zones increases. Okay. Next is, why is cold working performed prior to artificial aging in the 2024 aluminum alloy? So cold working, so the cold working with artificial aging is the T8 temper condition. So this is the solution heat treatment plus cold work plus artificial aging. So before artificial aging, we do some cold deformation. So cold deformation means the cold work deform the sample, deform the deformation increases dislocation density in alloy in supersaturated solid solution, and this dislocation density uh, further increases grain boundaries also. Grain boundary. So this dislocation density rho and grain boundary d as it increases. So this provide heterogeneous nucleation sites, nucleation for precipitates. So with heterogeneous nucleation sites, more precipitates will form, and with high density of precipitates, the strength will further increases in the 2024 aluminum alloy. Next question is, so cold working is done to provide the heterogeneous nucleation site for more precipitates nucleation. Next question is, what characterizes the morphology change of GP zones in 6000 series alloy as aging progresses? So the in 6000 series alloy is the aluminum, magnesium, silicon. So the uh, precipitate formation step for this aluminum magnesium silicon alloy is first supersaturated solution transform into GP zones, and this GP zone transforms into the beta dash precipitate, which is composition is Mg2Si, and this beta dash, so this is metastable. uh, from metastable to equilibrium phase, beta is formed. So beta is also Mg2Si. So after GP zones, beta prime and beta uh, phase form. So beta is the equilibrium phase. So the morphology of GP zones initially are the spherical, and as it grows with beta, so elongate. So these spherical precipitates elongate in beta dash along in 100 direction, and after that further growth, beta form is needle shaped. So its morphology changes from the spherical precipitate to elongated and needle shaped precipitates of the Mg2Si. Next question is, what is primary difference in the precipitation sequence when magnesium is added to an aluminum copper alloy? So when magnesium is added, let's see, we take a, aluminum alloy of 2024, which has composition of aluminum 4.4 copper, 1.5 magnesium, and zero point 0.8 manganese. So the magnesium atom also form precipitate with the copper atoms. So cluster of magnesium and copper starts to form first. Cluster of copper and magnesium leads to the formation of GP zones from supersaturated solution. Then, so from supersaturated solution, the GP zones of copper and magnesium atoms form. After that, the S dash precipitate form precipitate form with the composition of Al2CuMg. Then further with growth, the S equilibrium phase of precipitate form, which is also the Al2CuMg, and this is the equilibrium phase. So in with addition of magnesium, the precipitate composition changes from CuL2 to Al2CuMg. So similarly, we can add iron and silicon also. So we can reduce the iron silicon addition in the aluminum copper alloy to ensure the high fracture toughness. Next question is, what is the typical artificial aging temperature range for 6000 series alloy, and why is this range chosen? So for the 6000 series alloy, aluminum, magnesium, silicon, the 170 to 220 Celsius temperature range is chosen. So this is temperature range provides the formation of GP, means the aluminum MgSi precipitate GP zones form in this region only because it needs the high diffusion. So with at this temperature, the GP zones and sorry, GP zone solvus is around 226 degrees Celsius. So the magnesium and silicon solubility decreases fast with decreasing the temperature from the 226 degrees Celsius to so generally we keep the one temperature up to 170 to 220 degrees Celsius, so the magnesium and silicon atoms can diffuse effectively to form the GP zones. Sufficient diffusion rates to form GP zones from supersaturated solution, then only beta dash and beta uh, precipitate form. So next question is, how does the addition of copper above 1% influence the precipitation behavior and properties of 7000 series aluminum copper alloy? So first we know that the aluminum 7000 is the aluminum and zinc. So aluminum in aluminum and zinc, the supersaturated solid solution first form GP zones, then neta dash precipitate of metastable state form. So this is the MgZn2 precipitate. And after that, equilibrium phase neta form of this same MgZn2. So this is the equilibrium phase. So so in the shape of the this neta dash and neta is also first is the spherical, and after that with the formation with further coarsening, the plate shaped neta equilibrium phase are formed. So if we add one copper in aluminum zinc alloy, so let's consider a 7075 aluminum alloy. So its composition is aluminum 5.6, 5.6, zinc. Then it has 2.5 Mg magnesium. Then 1.6 copper is there, and with 0.23 chromium. So the one if we add more than 1% copper, so in aluminum, the maximum solubility at room temperature of copper at room temperature is only 1%. But as it is greater than 1%, the extra copper atoms uh, extract out from aluminum matrix and helps in forming the GP zones and form GP zones. So the extra copper will go into the GP zones and changes the composition of the uh, equilibrium phase and the precipitates. So the copper in precipitates provide good stress corrosion resistance. Sorry, stress corrosion resistance. Next question is, so the copper in it changes the composition of the precipitates that increases helps in the uh, improving this stress corrosion resistance of the 7000 series aluminum alloy. Why it is critical for GP zones to form uniformly before the main strengthening precipitates develop. So, uh, so for the 7000 series alloy, first we form GP zones at 115 to 130 degrees Celsius aging temperature for the homogeneous for the uniform formation of the GP zones. So this temperature provide enough thermal gradient or undercooling because this temperature provide sufficient undercooling uh, to to form homogeneous nucleation. In the grain. So this homogeneous nucleation of GP zones stops or retard the brittleness. So means if we don't form GP zone and in this is the temperature range, so the for precipitates will form around the dislocation and grain boundaries. So these precipitates will at the grain boundaries lead to the intergranular fracture and reduces the ductility of the 7000 series alloy. But so to in homogeneous nucleation, the small GP zones created within the grains uniformly, and after that we do second step aging. So after formation of GP zones, temperature is increased for increased to accelerate the growth. So, but first, the uniform precipitation of the GP zones are done. Then, after the uniform homogeneous nucleation. These GP zones are further coarsened to form the final equilibrium precipitates by coarsening them. So first the GP zones are formed at low temperature, then coarsened at high temperature. So the so for the 7000 series, the general heat treat, aging we temperature is at 120 degrees Celsius. Aging at 120 degrees Celsius for 1 hour. Then after that, 160 to 175 degrees Celsius coarsening. Next question is, in the context of 6061 alloy, what is the significance of the T6 temper condition regarding its mechanical properties? So the T6 temper in it T6 temper is solution heat treatment plus cold work, or no, uh, means aging. This is artificial aging up to peak hardness. So the T6 temper provides the yield strength up to 275 MPa. So this T6 temper increases its yield strength of the 6061 alloy. So that's why this temper is generally preferred for this 6061 alloy. And this because of this high strength yield strength, this is generally used in architectural applications. Okay, so next question is, so what is the purpose of employing a two-stage aging process for 7000 series alloy like 7075? So it is just same as previous. So the first stage at 120 degrees Celsius provide homogeneous nucleation of GP zones and to avoid preferential growth on grain boundaries and dislocations. Means if we directly age at a single temperature, so the nita precipitates will directly form on grain boundaries and dislocation. So to avoid this preferential growth on grain boundaries and dislocations, we first provide homogeneous nucleation at 120 degrees Celsius, and in the second stage at high temperature 160 to 175 degrees Celsius. These precipitates uh, coarsen to form uh, equilibrium phase. So this by this method we can maintain the ductility with this operation, with this two-stage aging process. So next we will go to the assignment, previous assignment questions. So first question is that uh, for precipitates to form in an alloy. So first option says solute atoms should have limited solubility in the parent metal at room temperature. Yeah, so first is correct. Next say solute atom should be insoluble in the parent metal at elevated temperature. So this is wrong. Solubility of solute atoms should not change with temperature. This is also wrong. Solubility of solute atoms should increase with increasing temperature. Yeah, this is correct. But first, solid, yeah, both A and D is correct. So, solute atoms should have limited solubility in the parent metal at room temperature, and the its solubility increases with increasing temperature. Next is the second question: increase in strength due to coherency strain of precipitates and matrix will be related to volume fraction as. So for coherency strain, the delta sigma is written as 6g r by b raised to power half, then f power half and epsilon power 3 by 2. So the f is the fraction of precipitates, so it is 1 by 2. So the correct option is uh, C. What does T4 temper in aluminum alloy refers to? So T for temper is the solution treated plus natural aging. So first is correct. And next question is, in which of the following case of quenching medium precipitates are much finer if the alloy is subjected to same solution aging and aging temperature? So we have to tell according to the cooling rate speed. So air cooling, forced air cooling, water quenching, and oil quenching. So, in which following case of quenching medium precipitates are much finer if the alloy is subjected to same solutionizing and aging temperature. So, water quenching, air cooling, and oil quenching provide the finer precipitates. So, A, C, and D is correct. Fifth question is strength and hardness of the aluminum alloys decrease during overaging heat treatment because of, so in strength and hardness. So with overaging heat treatment, the finer precipitates coarsen and the number of precipitates decreases and the size increases, and also the distance between two precipitate also increases. So that lead to coarsening of precipitate. The distance between them increases and the number of densities of precipitate also decreases. So that lead to decrease in strength and hardness. Next question is, when precipitates shear out by dislocation, then strengthening due to an increase in surface energy is, so it is asking which relation it have with the volume fraction and particle metric surface energy. So we will first write the uh, equation. So the strengthening due to shearing of precipitate is written as 2 square root of sigma divided by and gamma s and the f by r. So here gamma s is the surface energy between particle matrix between particle and matrix, and f is the volume fraction of precipitates. So it is directly proportional to volume fraction and directly proportional to the uh, particle metric surface energy. So A and C is correct. Next question is, when the aluminum alloy aged beyond the peak aging time, then strength and hardness of the alloy increases but ductility decreases. No. Strength and hardness of the alloy decreases but ductility increases. So, yeah, so this is correct. Interparticle spacing increases. So B and C is correct. Next question is, when dislocation moves through the ordered precipitates, then strengthening will occur mainly due to the formation of. So in ordered precipitate, when dislocation move, it creates the antiphase boundary. So that antiphase boundary surface energy increase the strength of the material. Then next question is, which of the following is the correct precipitation sequence for aluminum copper alloy when subjected to artificial aging? So first is supersaturated solution form that leads to GP zone 1, GP1 zones, then theta double prime forms, after that theta prime form and theta form. So which B option is looking correct. Next question is, what does T652 temper in aluminum alloy refers to? So we have seen a question with T651. So T651 is the solution heat treatment plus artificial aging plus stress relieving by compression. Sorry, by stretching. Stretching to remove compression. Just yeah, to remove compressive residual stress. But in T652, we do solution heat treatment plus artificial aging plus stress relieving by compression. By compression to remove tensile residual stress. So it is solution heat treatment plus artificial stress relieving by compression. So D option is correct. Next question is uh, when precipitates shear out by dislocation, the strengthening due to an increase in surface energy is so this is the so it is directly proportional to volume fraction of precipitates and they're directly proportional to interparticle particle matrix surface energy and inversely proportional to no particle. So A and C is correct for this. Next question. When the aluminium alloy aged beyond the peak aging time, then strength and hardness of the alloy decreases but ductility increases, interparticle spacing increases, and coherency strain between matrix and precipitate also increases. What are the necessary conditions for precipitates to form in an alloy? So solute atoms should have some solubility in the parent metal at room temperature. This is correct. Solid solute atom should be soluble in the parent metal at elevated temperature. This is also correct. Solubility of solute atom should not change with temperature. Sol solute atom should increase with increasing temperature. So A, B, and D is correct. Fourth question is small amount of lead and bismuth are usually added in 6000 series aluminum alloy too. So the lead and bismuth are added in the 6000 series aluminum, silicon, and magnesium alloy. So this increases the machinability of this alloy or this series alloy. So first option is correct. Next question is increase in strength due to coherency strain of precipitates and matrix will be related to misfit strain. So coherency strain, we have write the equation delta sigma. We have written the equation 6G R by B raised to power half. F is 1 by 2 and epsilon is the 3 by 2. So epsilon is the coherency strain. So it is 3 by 2. So first option is correct. Next question is, what does T651 temper in aluminum alloy refers to? So it is the solution treatment plus artificial aging plus stress relieving by stretching to remove compression residual compressive residual stresses. In the next question, which of the following mechanisms are responsible for strengthening due to precipitations? So, when precipitates form, which strengthening mechanism are responsible uh, to increase the strength? So, coherence strain between matrix and precipitates, yes. Or one looping around the precipitate in overage condition, this is also correct. Change in interfacial energy due to particle shearing, this is also correct. And local change in the modulus due to different precipitates. This is also correct. So all four options create strengthening in precipitation hardenable aluminum alloys. Next question is, strengthening of T4 treated aluminum alloys mainly due to the formation of. So T4 temp is the solution treated plus natural aging. Solution treatment plus natural, sorry, solution heat treatment plus natural aging. So with natural aging, the driving force to form the to nucleate the precipitate is less. So GP zones will form, and then they grow in size. So equilibrium precipitates. Only the green boundaries are the sites on which can provide the less driving force to form the nucleation, form the precipitates. So the equilibrium precipitates on green boundaries are formed, and GP zones and solid cluster also create with the time. Next is a slow cooling from the single phase region in an age hardenable alloy will result in. So slow cooling from the single phase region, slow cooling leads to coarse particles, while fast cooling leads to fine particles. Next question is, which of the following statements are correct about the GP2 zones in 2000 series aluminum alloys? So GP2 zones are the alternative arrangement of aluminum copper alloys along on 100 planes. So GP2 zones are alternate layers of copper and aluminum atoms on 100 plane. This is correct. GP2 zones are smaller than GP1 zones, but their number density is higher. No, number density decreases. GP2 zones are larger than GP1 zones, but their number density is lesser than GP1 because GP1 are higher density, and with time they coarsen to form the GP2 zones. So with coarsening, the number density decreases and their size increases. So this D option is correct, and GP2 zones have disc-like shape and tetragonal crystal structure. So this is also correct. Yeah, so this is all for today. We'll discuss further in the next class.